So let's take a look at this dilution problem. So oftentimes in the lab, they'll ship to you or send you a solution of high concentration, maybe like 12 molar hydrochloric acid, and then you want to dilute it down so you can get the concentration that you want. And dilutions basically means you just add water to that. So let's take a look at this example right here. It's a what volume of 3.5 molar sodium hydroxide. So say I have a bottle of sodium hydroxide solution. So this is your stock solution, the solution that you start off with. So oftentimes we'll call this the stock. And I want to figure out how much I need to take out and put it into a different flask, maybe a volumetric flask, something like that, to come up with 50 milliliters, that's 0.5 molar. So I want to take some of this out, and then I put it into another flask. That's 50 milliliters, that's 0.5 molar. With that, very common thing to do in the lab, whenever you have a dilution problem, we use a dilution equation, and that's going to be M1 V1 times M2 V2. M1 and V1 are from the higher concentration. So in this case, it's going to be this right here. So the molarity of the first concentration is always going to be higher than the second. So that's where you start off with. That's your stock solution. So a couple of things in case you get confused. M1 is always greater than M2. This is your diluted solution. This is what you start off with. So the M1, V1 are your molarity and volume. And when I say V1, it's how much you take out. This is your M1. It's how much of that 3.5 molar that you take out, and then you dilute it down, etc., with water, as the case may be. M2, V2, M2 is the concentration of your diluted solution. So that's a 0.5 molar. And V2 is your total volume after you dilute it down. Again, just like if you're making concentrated orange juice, you buy the concentrated package, that's going to be your M1, V1. You dump that into like a 1 gallon container and you dilute it with water. So after you dilute it down, that's your M2 and then your V2. Same thing if you buy concentrated pesticides like Roundout or something like that, and you dilute it down, etc. So a couple of things with this. Let's just kind of write down what we got. I know that M1 is 3.5 molar. V1 is what we're looking for. We're looking like how much V1 do we need to take out to do that again. It's not how much is in a total solution or in that container, but how much I have to take out. M2 now, 0.5 molar, and then V2 is my total volume. That's 50 milliliters. A couple of tricks when you're doing this. M1 is always greater than M2. So 0.35, 3.5, and 0.5. So it's always going to have a higher concentration. In terms of V1 and V2, V1 is always going to be a lower amount than V2. Because V2 is how much total volume you have at the end. V1 is how much you take out. So let's just go ahead and just solve for V1. So V1 is M2 V2 over V1. Let's just plug everything in. So M2 V2 over M1. Sorry about that. So 0.5 molar times 50 milliliters divided by 3.5. Notice that your molarity cancels out, so you don't have to convert that volume to liters. When I do that, I'm going to end up with 7.14 milliliters. So basically what that means is I got to take out 7.14 milliliters, add it to this flask, and then dilute with water until you get 50 milliliters total. So again, you have to add the rest for water. So whenever you have a dilution problem, again, it's very common in the lab, always use a dilution equation. M1 V1 is equal to M2 V2. This second one, we're going to look at the concentration of potassium ions and 1.5 molar potassium phosphate. So I got 1.3.5 molar potassium phosphate. This is soluble. So this is soluble in water. Remember, potassium solutions are going to be soluble in water. So let's kind of write this out. So this is going to break down. This is where it's kind of like net ionic equation. This is going to break down to potassium and phosphate ions. So potassium and phosphate ions. So this is what's actually in solution. Now, to balance it, I got 3 potassiums here. I need to put 3 right there. Again, this is going to be 1. So again, this is just another mole to mole ratio. Basically, what it means is 1 mole of potassium phosphate will produce 3 moles of potassium ion. So the concentration of potassium ion is going to be 3 times that of the potassium phosphate initially. So let's just write down what's given. So 1.50 when they say molar concentration, same thing as molarities. This is another way of saying it. I need to get to potassium, so it's a 1 to 3 ratio. 3 moles of potassium ions is equal to 1 mole of potassium phosphate. So when I work this out, I'm going to end up going to get 4.50 moles per liter, or 4.50 big M potassium ions. One last thing, whenever I see a big M like this, always break it down to moles per liter when you do these problems.